This talk is about somatosensory evoked potentials, technical issues. It is the second talk on this topic. This talk is intended for the Nicklaus Children's Hospital Clinical Neurophysiology Fellows. It will be conducted in a question and answer format. The first question: which of the following factors influence somatosensory evoked potentials? A. Cooperation. B. Drugs. C. Age. D. All of the above. Somatosensory evoked potentials relevant features include latency, amplitude, and morphology. These parameters are influenced to a different degree by age, height, gender, drugs, cooperation, temperature, stimulus, and filters. Age was addressed in a prior video in this same series titled Pediatric Somatosensory Evoked Potentials. Also addressed in a prior video in this series was stimulus. This was addressed in the video called Cutaneous Stimulation. So the answer to this question is D. Next question: height and arm length influences central nervous system conduction during upper extremity and lower extremity somatosensory evoked potentials. A. True. B. False. This frame shows the factors that influence somatosensory evoked potentials. This question refers to height. Central conduction time of the lower extremities somatosensory evoked potential, which is defined by most neurophysiologists as the time interval between the lumbar potential and the cortical potential, is affected by height. The absolute latency to N37 following posterior tibial nerve stimulation at the ankle is certainly affected by height, as you can see. From 5.2 feet to 6.2 feet, there is a 6 millisecond difference. In this new frame, central conduction is being considered. As you can see here, conduction is being estimated from the lumbar potential to the cerebral cortex. An interval often considered as central conduction. As you can see, from 5.2 feet to 6.2 feet, the average increase is about 1 millisecond. Yet, despite this minimal increase, the text in electrodiagnosis medicine states that height makes a difference in central conduction when gathered in the course of performing a leg somatosensory evoked potential. Upper extremity central conduction time measured from N13 to N20 does not change with increased height. So the answer to this question is B. Next question: the usual EEG filter settings are low frequency filter 1 Hz, high frequency filter 70 Hz with roll-offs of -6 dB per octave. A. True. B. False. This frame has the parameters that are used for EEG filtering. a low frequency filter of 1 Hertz with a roll-off of -6 dB per octave, and a high frequency filter of 70 Hertz with a roll-off of -6 dB per octave is the usual setting. It is important to stress that the notch filter may be used during EEG recording, but preferably it should not. So the answer to this question is true. Next question. What filter setting should not be used for somatosensory evoked potentials? A. Low frequency filter of 1 Hertz, high frequency filter of 70 Hertz. B. Low frequency filter of 30 Hertz, high frequency filter of 3000 Hertz. C. Low frequency filter of 5 Hertz, high frequency filter of 1000 Hertz. D. Low frequency filter of 20 Hertz, high frequency filter of 4000 Hertz. I am going to start answering this question by going back to the general figure that lists all the factors that influence somatosensory evoked potentials. In this question, I will address filters. Please view other videos in this channel on the subject of filters. Your ability to understand the current discussion will be much improved if you do so. The appropriate filters for somatosensory evoked potential is a matter of debate. Chiappa's book recommends low frequency filters ranging from 1 to 30 Hz and high frequency filters of 3000 Hz. Kruku recommends a low frequency filter of less than 3 Hz and a high frequency filter of 2000 Hz. In Dumutru's electrodiagnostic medicine, there are two recommendations. One is to use a wide band pass with low frequency filter of 0.1 Hz and a high frequency filter of 5000 Hz. The second recommendation is to use a low frequency filter of 1 to 10 Hz and a high frequency filter of 3000 Hz. The 2008 recommendations from the Academy advises us to use a low frequency filter of 30, but explains that you may need to go as low as 1 Hz, and that will be okay, and a high frequency filter of 3000. The next table I will show you from an article by Dumitry and Walsh recommends the following. It recommends a high frequency filter setting of as low as 500 Hz. So the answer to this question is A. Next question. Cutoffs can be given in percentage or dBs. A true, B false. Here are represented the typical filter settings that we use for somatosensory evoked potentials, which is 30 for low frequency filter and 3000 for high frequency filters. It is important to remember that no notch filter should be used during somatosensory evoked potential gathering. This drawing shows the bandpass achieved with the previously mentioned filters. As you know, filters are labeled according to their cutoff. The cutoff of a filter is given by the frequency of the wave, it decreases by 30% of its original amplitude. Here we are depicting a 30 Hz low frequency filter because the filter reduces to the amplitude of 30% a 30 Hz wave. Slower frequency are reduced by more than 30%, and frequencies above 30 Hz are reduced by less than 30% of their original amplitude. Filters cannot be conceptualized without knowing the roll-off of the filter. This is so because the roll-off foretells how much above and below the cutoff level a filter will reduce the amplitude of the given waves. I will address the roll-off a little later, but for now I want to go back and to concentrate on cutoffs. As you can see in this frame, the cutoffs are represented as percentage of amplitude drop. Therefore, the cutoff can also be converted to dB. 3 dB corresponds to a power ratio of 2. Hence, minus 3 dB is equivalent to 50% drop in power. And since voltage is equal to the square root of power, and here power is constituted by 1/2, the square root of 1/2 is 70%. So 6 dB corresponds to 25% of power, which corresponds to 50% of voltage. Again, the cutoff of the filter in this frame are being represented by percentage, but they could equally be represented by dB at the ratio shown in this frame. So the answer to this question is true. Next question. A 1 Hz wave is more likely to be reduced by a low frequency filter of 30 Hz with a roll-off of minus 18 dB per octave than by a low frequency filter of 30 with a roll-off of 6 dB per octave. A true, B false. This frame represents a low frequency filter of 30 Hz with a roll-off of minus 12 dB per octave. For now, let's forget about the high frequency filter. I have now color cream the bands pass to show you the consequence of using this filter. Notice that the roll-off is minus 12 dB per octave. Now I have changed the roll-off of the filter to minus 18 dB per octave, thus making the incline more stiff, as I have represented by displacing the dashed red line in this frame. This adjustment will cause a change in the band pass of the filter, which consists of more reduction of the amplitude of waves below the cutoff frequency and less reduction in amplitude of the wave above the cutoff frequency of the filter. So a new bandpath will be produced to reflect the changes that has taken place in the roll-off from 12 to 18 dB per octave. Now, if instead of minus 18 dB per octave, we use a filter of minus 6 dB per octave, as we have represented in this frame by increasing the tilt of the red interrupted line, the bandpass will change accordingly, So wave with a frequency of less than 30 Hz will be less reduced in amplitude, and those above the cutoff frequency will be more reduced in amplitude. This frame compares the different bandpaths that will result from using filters of similar cutoff but with different roll-offs. Please stop the video and take a few seconds to study it. So the answer to this question is B. Next question. The maximal fundamental frequency of an ultimate wave corresponds to the contributing waveform maximally represented in the ultimate wave. A true, B false. This is the general frame which I have shown you in the past. As you can see, filter is one of those factors that influence the latency, amplitude, and morphology of the somatosensory evoked potentials. To select the right filter for a job, we need to know two things. The maximal fundamental frequency of a waveform, which is a function of the wave composition of the wave we are studying, and the slope of the curve at the location of marking latency measurements. As we said, the first issue is to determine the maximal fundamental frequency of the wave to be studied. I'd like to start by asking you to look at this wave, to which I will refer, as you know, as the ultimate wave, since it is the one we see in the screen of the computer when we do a test, and to try to determine its maximal fundamental frequency. As you know, the ultimate wave is made of other waves. Taking that the duration of the wave represented in this frame is 1 millisecond, and the relation to the ultimate wave, we can calculate the frequency of the contributing waves. For V1, the frequency would be 1000 Hz. For V2, the frequency would be 3000 Hz. And for V3, the frequency would be 5000 Hz. Thus, the maximal fundamental frequency of the ultimate wave is 5000 Hz. Next, we need to know its proportion in relation to other frequencies. In other words, we need to know how many of the different Hertz wave constitute the ultimate wave. So the answer to this question is B. Next question. The latency of all waves studied in neurophysiology are measured at their peak. A true, B false. The second step we need to take to choose the right filter is knowing where we're going to measure latency. So once we know the waveform composition, mainly the fundamental frequencies present in the wave, their proportion, and the maximal fundamental frequency, we need to know the slope of the curve at the location where the latency marking needs to be taken from. The latencies of the waves are either measured at the onset or at their peak. In order to accurately measure onset latency, we need to let the maximal fundamental frequency in the wave we are studying to go through unimpeded. In order to measure peak latency, we need to use filters that would allow all maximal fundamental frequencies to go through, but a reduction in the amplitude to a high degree will not interfere with accurate markings. On the other hand, it is important when measuring peak latency to let the lower frequencies in the wave to go through unimpeded. I will give you an example in the answer to the next question. So the answer to this question is false. The fundamental frequencies that make up any of the waves we see in the screen of a neurophysiological test, that is, any ultimate wave, is debatable. I have come to this conclusion because the values given by different authors do not coincide. I will give you some examples. In this frame, I have placed the frequencies in the y-axis, and in the x-axis I will place columns corresponding to different neurophysiological tests and the books they come from. In the book titled ENG Secrets, the value given for the sensory nerve action potential fundamental frequencies are from 0 to 3000. And for compound muscle action potential from 0 to 500 Hertz. And for somatosensory evoked, the figures given are the same as those for sensory nerve action potential. In Jasper book, the values given for fundamental frequency of somatosensory evoked potential is from 20 to 3000. In Dumitri's electrodiagnostic medicine, in the highest frequency in somatosensory evoked potential, which correctly they point out that is present at the rise time of the ear point and the popliteal fossa potential, is 800 Hertz. In this book, there is no mention of the lower margin that I could find. So, as you can see, the number of fundamental waves in somatosensory evoked potential has been considered by many authors, and they have arrived to different conclusions. The second issue regarding fundamental waves that I mentioned initially is the quantity of each of these frequencies represented in each ultimate wave. Thank God I only found one study regarding this issue. In this chart, in addition to showing the fundamental frequencies that make up the wave of a compound muscle action potential, it shows you the relative intensity of the different fundamental frequencies. Notice that in this figure, the compound muscle action potential fundamental frequencies are from 0 to 1000, but more importantly, that the fundamental frequencies most represented are slower than 300 Hertz. Now I have added to this table the fundamental frequencies that make up sensory nerve action potential wave. As you can see, the fundamental frequencies of the sensory nerve action potential, according to these authors, goes from 0 to 3000 Hertz, and the bulk of the fundamental frequencies are faster than 300 Hertz. So the answer to this question is B. Next question. The high frequency filter used for motor nerve conduction has to be higher than the filter used for somatosensory evoked potentials. A true, B false. I am sure that by now you can recognize this frame. So, regarding waveform composition, we have to consider the range of fundamental frequencies, quantity of the different fundamental frequencies, and the maximal fundamental frequency. Whereas regarding the slope of the curve, we need to know the location of the marking. That is the location in which we're going to measure latency. I will show you some examples. This is a compound motor action potential. Motor nerve latencies are measured to the onset of the compound muscle action potential. That is, as the wave rises. So the slope at this site is always more than 0. The fundamental frequency of compound muscle action potential, as we previously discussed, is from 0 to 500 Hertz. So the recommended high frequency filter is 10,000. This obviously sounds very high, and this is because, as we have previously mentioned, we want to have a good vertical resolution, and for that we need to make sure that the maximum fundamental frequency is allowed to go through unimpeded. Sensory nerve action potentials and somatosensory evoked potential have much higher maximum fundamental frequencies. According to most authors, this frequency is in the 3000 Hz range. Yet we can use much lower high frequency filters. This is so because we measure peak latencies in this study, for which horizontal resolution is most important, given that the slope at the point of marking is 0. It is for the reason that some neurophysiologists advocate using a low frequency filter of 0.1 Hz. And just to give themselves some wiggle room, they like to increase the high frequency filter to 5000 Hz. This certainly widens the bandpass. This is a suggestion which is present in Dumitru Electrodiagnostic Medicine in page 376. So the answer to this question is true. Next question. Baseline stabilization is achieved by increasing the low frequency filter. A true, B false. Change in the low frequency filter will significantly change some waveform parameters. I will initially use sensory nerve action potential to demonstrate these changes, since sensory nerve action potential and somatosensory evoked potentials waveforms share the location from which latency is measured. And also, according to some authors, they both have the same composition. The high frequency filter for this and for the subsequent waveform that I will present is indicated in this frame, and it is set at 10,000 Hz. Now I have added the parameters we are going to follow as a consequence of changing the low frequency filter values in their respective units. The letter pointed by the arrow will be used to indicate the changes for that given wave, and it will be represented in the table, as you can see. So using a low frequency filter of 1 Hz, as we're doing in this example, that is in example A, and a roll-off of about minus 6 dB, but the roll-off was really not mentioned in the paper where this is taken from, as far as I can tell. But I'm using minus 6 dB per octave because that was the type of filter most often used at the time that this paper was written. Be it as it may, with this setting, the onset latency was 2.6 milliseconds, peak latency 3.3 milliseconds. The duration of the negative wave was 1.4 milliseconds, and the amplitude of the negative spike was 65 microvolts. The amplitude was measured from peak to peak. The next wave, here labeled B, as you can see, was recorded using a 10 Hertz filter, and now I have included in the row all the values for the different parameters. The next wave from C, is now being represented in the table, and as you can see, the filter used in this occasion was a low frequency filter of 100 Hertz. Again, I have added the values of the parameters obtained with this filter. Wave D, also represented in the table, was obtained using a low frequency filter of 300 Hertz. The impact of this filter is also represented in the new row. At this junction, I only want you to notice that the baseline of the waveform A fluctuates significantly, whereas the one of D is almost straight. So increasing the low frequency filter stabilizes the baseline as reflected in this frame. That is, decreasing the bandwidth at the expense of low waves stabilizes the baseline. So the answer to this question is A. Next question. Changes in low frequency filters modify peak latency but spares onset latencies in somatosensory evoked potential, sensory nerve action potential, and compound motor action potential. A true, B false. Here I have represented a model of low frequency filter. The narrowing of the bandwidth at the expense of a reduction of low frequency waves achieved by increasing the low frequency filter produces no changes in onset latency, as neither does an increase in bandwidth, which would result from decreasing the low frequency filter. Now, if instead of looking at the onset latency as we have just done, we look at the peak latency, we can see that decreasing the low frequency filter increases peak latency. So increasing the bandwidth by allowing more slow waves in has the effect of delaying peak latency, and on the contrary, increasing the low frequency filter, that is restricting the amount of slow wave contributing to the ultimate wave, decreases peak latency. I will summarize the effect of manipulating low frequency filters in the current frame. First, more or less slow waves in do not alter onset latency. Second, the more slow wave contributing to the ultimate wave, the more the peak latency will be delayed. And third, the fewer slow waves allowed in to contribute to the ultimate wave, the less the delay in peak latency will be. So in order to answer the question at hand, we need to ask ourselves, what about for somatosensory evoked potential, since before we were considering only sensory nerve action potential. So the question is then, will manipulation of the low frequency filter have the same effect on somatosensory evoked potentials? Given what I know about it, sensory nerve action potential and somatosensory evoked potentials have the same waveform composition. So I would say that I had never seen it written or tried myself by playing with the low frequency filters while doing a somatosensory evoked potential study, but my conclusion is that it will be the same for somatosensory evoked potential as it would be for sensory nerve action potential. The effect of low frequency filter manipulation has also been studied in compound muscle action potentials. Here we have waves corresponding to a compound muscle action potential. If we look at the column with the different low frequency filter settings and at the column with the onset latency, we can see that as far as onset latency is concerned, the changes in low frequency filter values do not produce any changes. Whereas if we looked at the column with peak latency values, we can see that the more slow wave allowed in, the more delay the peak latency will be, and the fewer slow wave allowed in, the less delay the peak latency will be. So the answer to this question is A. Next question. The lower the low frequency filter and the higher the high frequency filter, the more amplitude a wave will have. A true, B false. This is a representation of a low frequency filter. The arrow points to the low frequency filter column. So as you can see, allowing more low frequency waves in, as it occurs when we decrease the low frequency filter, increases the duration of the negative spike and the peak to peak amplitude of the wave. So we can say that the more slow wave in, the more the amplitude. The fewer slow wave in, the less the amplitude will be. In this frame, you can see the percentage of change which I have added in aqua color. Now I want to go and talk about high frequency filter. This is a representation of a high frequency filter. The more fast wave which is accomplished by increasing the high frequency filter, the more the amplitude of the wave. The fewer the fast frequency waves in, the less the amplitude. In this frame, again, you can see the percentage of change in amplitude produced by 9500 Hz change in high frequency filters. Now compare the degree of amplitude change that occurs as a consequence of the 9500 Hz change in high frequency filter that we have just mentioned to the degree of change that occurs with a change of 300 Hz in the low frequency filter setting. So as you can see, low frequency waves contribute more to the amplitude of a wave than high frequency waves. So the answer to this question is true. Next question. Changing the low frequency filter from 1 Hz to 100 Hz will decrease the amplitude of a sensory nerve action potential more than the amplitude of a compound muscle action potential. A true, B false. This is, as you know, a representation of a low frequency filter. I like to focus this time on amplitude. Using a 1 Hz low frequency filter, the amplitude is 65 microvolts in the first recording, that is in recording number A. When the filter is taken to 300 Hz, thus decreasing the number of a slow wave contributing to the ultimate wave, the amplitude is less than half of what it was when we were using a filter of 1 Hz. Using a filter of 100 Hz, the amplitude is also reduced. I have added in this frame the waveform composition of sensory nerve action potentials. As you can see, using a 1 Hz filter, that is a low frequency filter of 1 Hz, there is no significant impact in this potential. Using a filter of 10 Hz, the impact is also not significant enough to produce a drop in amplitude of the ultimate wave. When we increase the filter to 100 Hz, the impact on the potential is noticeable. There is a drop in the number of waves contributing to the sensory nerve action potential, which I have pointed out by making that area black. And when we increase the low frequency filter to 300 Hz, a significant portion of the potential is removed. At this point, we must ask ourselves if this is the same story with compound muscle action potentials. As you can see in this frame, the potential here being represented is a compound muscle action potential. Using a low frequency filter of 100, a significant number of waves are removed from the compound motor action potential. In this frame, you can see both potentials side by side using a low frequency filter of 0.1 Hz and now using a low frequency filter of 100 Hz. as you can see, the amplitude reduction in the sensory nerve action potential is 17%, whereas the reduction in the compound motor action potential is 48%. So the answer to this question is false. Next question. Changing the high frequency filter from 2000 to 500 will affect sensory motor action potential more than it would affect compound muscle action potential. A true, B false. This is a representation of a high frequency filter. This is a cartoonish representation of the bandwidth that would pass using a low frequency filter of 1 Hertz and a high frequency filter of 2000 Hertz with a roll-off of -6 dB per octave. In this frame, the consequence of decreasing the fast frequency filter to 500 is depicted. In this frame, as you can see, I have introduced the sensory nerve action potential obtained using different high frequency filters and the percentage of reduction as a consequence of manipulating the high frequency filter. As you can see, a high frequency filter of 2000 Hertz will not produce a significant amplitude drop when compared to when using a 10,000 Hertz filter as it was used originally. But using a 1000 Hertz high frequency filter will produce a rather large number of waves to be removed, which is reflected by a significant drop in amplitude of the potential. At this point, we must ask ourselves if the story be any different with compound muscle action potential, but this time with manipulation of the high frequency filter. So as you can see in this new frame, I have brought back the compound muscle action potential waveform composition and the different high frequency filters. A 2000 Hz high frequency filter will have no impact on the amplitude of the compound muscle action potential. And using a high frequency filter of 500 will also have very little effect on the ultimate waveform of a compound muscle action potential. So the answer to this question is true. Next question. The more fundamental fast frequency we remove, the more prolonged the onset and the peak latency will be. The more fundamental fast frequencies we add, the earlier the onset and the peak latencies will be. A true, B false. The ultimate wave is here represented by the broken magenta line. This wave is the product of a fast wave in aqua and a slow wave in yellow. The white line represents the peak latency. In this frame, I have depicted the consequence of removing the fast wave. Peak latency, as you can see, has been delayed. Now I have gone back to the original waves and added a fast wave, as it would occur by increasing the high frequency filter. the result of such a change will be that the peak latency would decrease. So the answer to this question is true. Next question. The more fundamental slow wave frequencies we remove, the shorter the peak latency will be. The more fundamental slow frequencies we add, the more delay the peak latencies will be. A true, B false. The ultimate wave is again represented by the broken magenta line. This wave is the product of the fast wave in aqua and the slow wave in yellow. The white line represents peak latency, as it did before. The removal of the slow wave will shorten latency, that is peak latency. Now I will go back to the original waves arrangement so we can see what happens to the peak latency when a slow wave, here represented in green, is added. As you can see, peak latency will be prolonged. So the answer to this question is A. Next question. A slow wave of 15 microvolts influences amplitude more than a fast wave of 50 microvolts. A true, B false. Here we have represented two fast waves of about the same amplitude, where another wave were to occur in the proximity of the faster wave, one a slow wave and another one a fast wave, here represented in aqua. The resulting waves depicted in green of the one influenced by the slower wave will be higher than the one influenced by the faster wave. So the answer to this question is true. Next question. Which of the following waves will be most impacted by increasing the low frequency filter from 30 Hz to 200 Hz? A. The air potential, B. N13, C. N19, D. N20. This tracing corresponds to a median nerve somatosensory evoked potential. I'd like you to focus on the derivation indicated by the arrow, that is CPI to the contralateral air point. I hope you've recalled this table from prior talks. Here, I only want you to focus on the derivation in question, which I pointed out to you before, which is CPI to EPC. In this derivation, the electrode 1 captures P13-14 and N18 potentials. And from the contralateral air point, no potential will be recorded. So the end result is that we will capture P13-14 and N18, which you can appreciate here in this frame, pointed by the arrow. Notice that the duration of N18 is much larger than the duration of the air point potential. it is also larger than N13 and then N20. As you can see, N18 is by far the one with the longest duration. Let's say that these derivations were obtained using filters with the above characteristics. That is the characteristic that you see in this frame. And then let's say that we want to modify the filters being used by increasing the low frequency filter to 200 Hertz. Or that we want to modify the study originally filter settings to decreasing the fast frequency filter to 1000 Hertz. So let's say that we want to do all the things and that we actually do them, and I will show you in the next frames the consequence of these changes. Using the original filter setting, the pattern of derivation we have discussed will appear. In this new panel, you can see the result of decreasing the high frequency filter, and here the result of increasing the low frequency filter to 200. As you can see, using this filtering, the N18 potential is almost gone, to the point that the machine is not able to mark it. Furthermore, notice that the amplitude of N18 went from 2.19 in the original settings to 2.15, which corresponds to a minimal drop in amplitude, and this has been the consequence of the decrease in the number of fast frequencies. But match that drop with what occurs when what we do with the filter is increasing the filter to 200 Hertz. As we previously mentioned, at 200 Hertz, N18 peak is no longer detectable. Now let's go back to the original filter setting and talk about peak latency. Using this setting, that is the original setting, the peak latency is 18.2. In this frame, you can see that the peak latency was increased as a consequence of decreasing the number of fast waves contributing to the ultimate wave, which resulted from decreasing the high frequency filter from 3000 to 1000. Now notice the amplitude of the air potential. That is not significantly less by removal of fast waves, but it is significantly less by decreasing the amount of a slow wave contributing to it. Regarding the peak latencies of this wave, you can see that using the original filter setting, the peak latency was 11.2 milliseconds, which became delayed by the removal of fast frequency waves and shortened by the subtraction of slow fibers. At this point, I will make a few more comments regarding N18. N18 is labeled in this flowchart of the different medial nerve somatosensory evoked potentials by the number 4. As we have mentioned during the course of this discussion about somatosensory evoked potential, in this video and also in prior video, the origin of this wave is likely to be the thalamus. But an equal sound argument can be made, and it is made by other authors, that consider N18 as arising from the tectum. This later explanation is based on the fact that some patients with thalamic infarct have preservation of N18. In this chart, I have stated other characteristics of N18. The characteristics are highlighted in this frame by making them aqua. If you have any questions about them, stop the video and take a few minutes to go over them. So the answer to this question is C. Thank you very much for your attention.